We haven't spent too much time with pendulums so far, primarily because that angle of the pendulum, it makes things a little bit more difficult to calculate. We do have one equation that we'll work with for a pendulum though, and that's the equation for the period of the pendulum. You can see here that period depends on the length of the pendulum and on g, that's the gravitational acceleration. So from that information we see that mass is not a part of this equation, so regardless of the mass of a pendulum, the period won't change. Now the length matters, amount of gravity matters, so if you were, say, taking a trip to the moon, you should definitely bring a digital watch rather than a grandfather clock to tell time, as it wouldn't be too useful once gravity changed there. Speaking of grandfather clocks, let's do that as our first problem. How long must a grandfather clock pendulum be to give it a period of 2.0 seconds? By the way, the period 2.0 seconds, that's so when it swings one direction that takes 1 second, and then back the other direction takes another second. So maybe a little counterintuitive that it's not 1 second for the period, but that'd be why. So our period is going to be 2.0 seconds, and that's equal to 2 pi times the square root of L over 9.8 meters per second squared. And then we'll divide both sides by 2 pi. And get 0.318 seconds. Is equal to the square root of L over 9.8 meters per second squared. We'll square both sides now. And get 0.101 seconds squared is equal to L over 9.8 meters per second squared. And then both sides times 9.8 meters per second squared. Gets us a length of 0.993 meters. So just shy, just a tiny bit shy, 7 millimeters short of 1 meter for a grandfather clock to have a period of 2 seconds, or 1 second back and 1 second forth. I wonder if there's significance to that relationship. The other part to pendulums that we need to talk about is something called the small angle approximation. The idea here is that if we look at the forces on this pendulum at some moment in time, we've got weight always downward, and we've got our tension force along the direction of the string. Now, if we broke that tension force up into the part of the tension force that pulls the ball back toward equilibrium, that part would be T times the sine of theta. And so whenever we talk about simple harmonic motion, we talked about how this restoring force that pulls our object back toward the middle, it has to increase proportionally with the distance away from equilibrium. Now here, that force actually increases proportionally with the sine of, not even the distance, but the angle from equilibrium. Now it turns out that if we choose theta to be very small, far less than 1 radian, then sine of theta is approximately equal to just theta. And T sine theta then just becomes T theta. So now our force is proportional to that angle, that angular distance away from equilibrium. And so some of the other assumptions that we make in making our calculations will be a little truer now. So for this equation to work, the equation for the period of a pendulum, we have to have in place the small angle approximation, that we only pull our pendulum back a little bit. Generally the guideline that I've seen has been roughly 15 degrees, though I'm not sure that there's any universally accepted limit for that, but far less than 1 radian to make this work.